right, in this section we're going to learn about coloring graphs, and we start with a statement of what used to be one of the most famous unsolved problems in mathematics. So consider the scenario where you're drawing a map. Maybe it's a map of the United States, or maybe it's a map of the world, but let's just consider a map of the United States. And each state is colored in, and if two states share a border, they make those states different colors. And it's been well known for a long time that if you only had 5 different colors available, that would be sufficient to color the map. But if you had just 3 colors to use, you would encounter maps where you were forced to color 2 adjacent states the same color. And what was unknown for a very long time was that what's the minimum number of colors you need in order to guarantee that you could color any map. We knew that 5 would suffice. We knew that 3 wouldn't, but we weren't sure if it was 5 or 4. And it has since been shown that 4 colors will suffice. I'll say that I'm pretty sure, I think the proof involved the use of computers. Like they were able to narrow it down to a finite number of cases, like maybe 1,000 or so cases. And they use computers to prove, to finish up the proof. So I'm willing to bet, like it would still be an interesting result if somebody were able to prove this without the use of computers. So coloring a map is a graph theory problem, and here's why. So here's a map, right? So I've got like some regions and boundaries. We can find a 3 coloring for it. That means that we can color this with 3 colors where no 2 bordering states or regions have the same color. So I'll say my colors are red, blue, and green. One way to do this is to just color the 2 side regions red and then alternate in the middle between blue and green. Right, so that will suffice. Now, in order to make a map into a graph, it might seem like we should make the boundaries into edges and then make every region into a face of the graph, right? Like imagine that we have like a vertex here and a vertex here. However, it is more convenient and useful to consider the dual of this graph. And here's what a dual is. If you have a planar graph and you've got some faces of that graph, you obtain the dual by making each face into a vertex, and then you construct an edge between the 2 vertices if the faces are adjacent, right? If they border each other. The outside face is included as a vertex if, only if it's going to be colored. So let's say here's my, the map. Here's the graph from the other region. So we've got these faces. I'll just label them A, B, C, D, E, and F. So the dual, I'm going to have a vertex for each face. And I'll use little lowercase letters, A, B, C, D, E, and F. And then I'm going to draw an edge connecting them if they share a border. So like I have to have edges going all the way down like that. And then E has to be connected to each of these vertices in the middle. And F has to be connected to all of these vertices in the middle. Here's another graph. We've labeled the faces here. In this case, we've labeled the outside face. We should note that. So that outside face will have a vertex. And note that the outside face borders all the other regions. So I'm actually going to put that vertex in the middle, and then the other vertices around it. So everything's connected to the outside face. And then B should be connected to C and D, and E should be connected to C and D as well. So it looks like this. So in this case, so there's actually, these graphs look kind of similar to each other. So now here's what we've done. When we consider the dual of a graph, the question of coloring two faces of a map is now changed to coloring two vertices, or coloring faces in general is changed to coloring vertices. And if two vertices are connected by an edge, they can't be the same color, right? So we've kind of changed this coloring a map problem to coloring a graph problem by saying we just need to color vertices, and if those vertices are connected by an edge, they cannot be the same color. So here's our strategy. We're going to use some counting techniques actually here. So we're going to start. Suppose we have, let's look at this graph, really simple graph, right? I got two vertices connected by an edge. And suppose we have 5 colors available, we're going to figure out how many colorings there are, like how many options, all right? So what we're doing now is we're changing this question of can we color it to how many colorings are there if I have a certain number of colors available. If the number of colorings available is 0, it means that we cannot color it with that many colors. So in this case we have 5 colors available, so let's pick a color for vertex A. There are 5 choices, right, because we got 5 colors. And then we'll pick a color for vertex B. Now we've already colored A, right? And A is connected to B, so that means that I can't color B the same color as A, so there are 4 choices left for B. And now we just follow up with the multiplication counting principle. There are 20 colorings, or 20 ways to color this graph if I have 5 colors. Okay, so let's do another one. Let's suppose I want to color this graph, and I have, let's see, 4 colors to choose from. So where we start probably matters. The number of vertices, that A is connected to is different than the number of vertices that C is connected to. So we're going to kind of go in a particular sequence. And in this case, I think I'm going to start with A. I'm going to start with vertex A and then just go maybe clockwise. So if I start with A, the beginning one is always easy, right? If there's 4 colors to choose from, I've got 4 choices. And then once we get to B, I've only colored A, B is connected to A, so that means I have 3 choices. Then clockwise, vertex D, D is connected to both B and A, and since I've already picked those 2 colors, that means that those 2 colors are no longer options, so I only have 2 choices. So now here we are, A, B, and D have all been colored, and I'm considering vertex C. C is connected to A and D, but it is not connected to B. So here's what that means. The colors for A and D, which we know are different from each other because they're connected, those 2 different colors cannot be chosen, but whatever color B is back in the running. So I can choose now, I have up to 2 colors, right? 2 choices for vertex C. And that gives us a total of 4 times 3 times 2 times 2, which is 48 colorings. Now, if I'm going to change this slightly and say maybe I'm not going to tell you exactly how many colors we have to choose from, and instead I'm going to say whatever that number of colors that I have to work with is lambda. So we have lambda colors available. Then if I go through the same process, right, how many choices for these, and I'm going in the same order. So I've got lambda choices for A. Once I've colored A, I can't use that again, so lambda minus 1. Once I've colored both of those, since D is connected to A and B, I can't use either, so that's lambda minus 2. But once I color C, once I get to C, there's lambda minus 2 choices again, right? A and D are no longer, I can't color the same color as A and D, but I could color it the same color as B if I chose to. So there's lambda minus 2 colors. And if I use the multiplication counting principle on this, I get an expression. Now, it's not just going to be a number, but it'll be an expression. Lambda minus 1, lambda minus 2, lambda minus 2. And this is what we call a chromatic polynomial. So we label it as C sub g for the graph of lambda. It's like a function. It's a function of lambda. If I know how many colors I have to choose from, if I know what lambda is, I plug it in, it tells me how many ways I could color it with that number of colors. For example, if lambda is equal to 4 and I plug it in, I will get 48. So just to kind of recap the first one, this is, we've already kind of stated this, but a coloring is a painting of the vertices, so no two adjacent vertices have the same color. So the C sub g of lambda is the number of colorings using lambda colors, and we call that the chromatic polynomial. It'll always be a polynomial. And then chi sub g, that's a Greek letter chi, is the smallest positive integer such that the chromatic polynomial is not equal to 0. Basically, it's the smallest number of colors that I need to have in order to be able to color the graph at all. So up here, I could tell just by looking at the polynomial here that chi sub g is 3. Like the presence of the factor lambda minus 2 means that if lambda is equal to 2, it's 0. Like I can't color it with 2 colors. So the minimum number of colors that I need is 3 here. So we're going to spend a bunch of time in this section figuring out how to find what the chromatic polynomial is for some graphs. Sometimes we could do it, we would say here in this case we found the chromatic polynomial by inspection. Like we could just sort of go around and then, by figuring out how many choices we have and then using the multiplication counting principle. Sometimes it will be a bit more involved, the process, but we're going to start actually by looking at 2 extreme cases that we're going to be able to use to kind of help us build more complex cases. So let's suppose I've got a graph that consists of 4 isolated vertices. That means there are no edges, right? There's my graph. And I have lambda colors available, and I want to find the chromatic polynomial, Cg of lambda. So if I go through just using the multiplication counting principle, how many choices for A, I've got lambda choices for A. A isn't connected to anything, so once I get to B, I still have lambda choices for B. C and D, there are no edges, right? I have lambda choices for all of them. They can all be the same color for all I care, right? So then using the multiplication counting principle, Cg of lambda is just lambda to the 4th power. And the chromatic number, chi g, is equal to 1, right? I only need one color because, nothing's connected to anything. So this is one extreme. If there are no edges drawn, you only need one color, and if there are no edges and you have n vertices, your chromatic polynomial is just lambda to the n power. Now let's look at the other extreme. What if all possible edges are drawn? So let's consider the complete graph with 5 vertices. We could draw it if we want, just to kind of remind ourselves what it looks like. But I have 5 vertices. Even if we aren't looking at it, though, we could figure out what the chromatic polynomial is, because every vertex is connected to every other vertex. That means once I use a color, I cannot use it again for any other vertex. So if I go through, let's say I'm starting at vertex A and I have lambda choices. Now I'll move to vertex B. I have lambda minus 1 choices. Once I move to vertex C, I have lambda minus 2 choices. I can never use a color again, which means I always have to subtract 1 from the number of colors that are available. So there it is. There's all 5 vertices colored, and I've got the product. Seen here, not lambda minus 3 twice, my last factor is lambda minus 4. And if I had only 4 colors, I couldn't color this graph, right? Because that would make that factor, lambda minus 4 equal to 0, and so the number of ways to color it with 4 colors is 0. That means that the chromatic number chi k5 is 5. And that makes sense, right? If I have 5 vertices and everything is connected to everything else, I need 5 colors. Some results here. Say we have a graph that is the union of its components. Remember, components are maximal connected subgraphs. If I have the chromatic polynomial for each of these subgraphs, for each of these components, then I can get the chromatic polynomial for the graph just by multiplying. That kind of makes sense because for every coloring of one component, you know, I've got that many colorings for the next component. Like we just sort of use the multiplication counting principle because the components themselves are not connected to each other. Right? So if I have 3 ways to color G1 and 2 ways to color G2, since they're not connected, then for each of the 3 ways I have to color G1, I have 2 ways to color G2, and we just multiply to give us 6. And a result of that is that the chromatic polynomial, like CG of lambda is 0, if and only if it's equal to 0 for one of its components. Like if I can't color a component, I can't color the graph. And the 4-color theorem is basically saying that CG of 4 is not 0 for every planar graph. Now, we just looked at a graph where CG of 4, we said, oh, look, this will be 0, but remember, K5 is non-planar. That was one of the results from the last section. And then just a corollary here, if it requires K colors to color G, then that means it must require K colors to color one of its components. It's sort of like a weakest link, like however number of colors you need to color one of the components, you need at least that many colors to color the graph itself. All right, next we're going to define a couple of graphs related to G. Actually, only one of them is a subgraph. So the G sub E hat here, this is a subgraph. The G mod E is not necessarily a subgraph. But here's how we make these graphs. So first of all, I have to pick an edge that exists in G. And then G sub E hat is just the edge where, is the graph where we just remove that edge, but we leave the vertices. So in 518 here, the graph on the left, let's say I call this graph G, and we've identified this edge that connects vertices A and B. So G sub E hat is just the graph where I'm going to take that edge out, but leave everything else. Over here, if this is the graph G, then G sub E hat, it has all the same vertices and almost all the same edges except for that one. Whoops. That's A. Okay, so that's G sub E hat. Now the other graph, which is not necessarily a subgraph, is G mod E. So when we mod out by an edge, here's what we're doing. We're removing the edge, and then the vertices on either side, we say that they are identified, meaning like we just sort of squish them into one vertex. So returning to this example, the graph on the left, we removed the edge E, and we got this graph here on the bottom that we drew. Now if I mod out by this edge, I'm going to take A and B and sort of squish them into the same vertex. And I guess I'll just call it A, but you call it A or B or whatever. But there is the graph G mod E. Now here, if I, on the right, so I've removed the edge to get G sub E hat, and if now I identify these, if those become the same vertex, just imagine kind of pushing A up so that it becomes the same as B. Now we're also going to lose some edges, right? I don't need, an edge going from F to B and F to A. I'm just going to have a single edge going from F to that one vertex that we have. Same as going from C to that one vertex. And in this case, G mod E looks like I'll call this vertex A. You can call it A or B, but note that as long as I had a vertex, if I had an edge going from one of the vertices, like if I'm looking up here at this graph, if I had an edge going from one of those two vertices, A and B, to another vertex, I include that. So I had an edge going from vertex D to B. So I've maintained that edge. I've had a vertex going from F to B and F to A, so that became a single edge here. So in this case, the graph on the right, G mod E, is a subgraph of G. The graph on the left, though, G mod E, is not a subgraph of the original. Okay, so now we have a result that's going to help us, that will eventually help us find a chromatic polynomial for some graphs. And the way we do it is by relating the chromatic polynomial of a graph G with the chromatic polynomial of the two related graphs that we just examined. So in Theorem 519, the chromatic polynomial for G sub E hat is equal to the sum of the chromatic polynomials for G and for G mod E. So note that when we defined these two graphs, G sub E hat and G mod E, we said, suppose we have an edge E, right, that connect a couple of vertices. So we're going to let E be the edge, and we'll just say it connects vertices A and B. And let's suppose we have a coloring for G sub E hat. So remember that G sub E hat, that's the graph with the edge removed, but the vertices stay. And G mod E is the edges removed and the vertices are identified, sort of squished together. And G is, of course, the original graph. So we're going to suppose we have a color for G sub E hat. Now, if these vertices A and B, which remain in G sub E hat, right? So G sub E hat does not have that edge drawn between A and B, but it does have both vertices. So if A and B are not the same color, then that means this is also a coloring for G, right? G is what we get if we take G sub E hat and just put the edge back. So if A and B are not the same color, then if I draw that edge connecting them, it's still a coloring for G. And vice versa. If I have a coloring for G, certainly I can color it. That coloring for G will also be a coloring for G sub E hat. Like, if I have a coloring for G, that means that it's fine if those vertices are connected. So if they're not connected, it's still going to be a coloring. Now let's consider the possibility that A and B might be the same color. if they're the same color, then this coloring is also a coloring for G mod E. It can't be a coloring for G if I put the edge back in there, right? Then if A and B are the same color, that's not a valid coloring. But it is a coloring for G mod E. Remember, G mod E, A and B are the same vertex, so clearly it's the same color. And vice versa. Any coloring for G mod E will also be a coloring for G sub E hat. I can make them, split them into the two vertices as long as they're not connected, right? Because they'll be, that they can be the same color if they're not connected. So now here's what we have. Any coloring for G sub E hat is either a coloring for G or for G mod E, but can't be a coloring for both. And now using the basic addition counting principle, right? These are non-overlapping. It's going to be a coloring for one or the other, but not both. That means that the chromatic polynomial for G sub E hat is the sum of the chromatic polynomial for G and the chromatic polynomial for G mod E, which is what we wanted to show. Okay, so our next result is that for any graph with n vertices, its chromatic polynomial will be an nth degree polynomial. Now, this might seem a little bit obvious when we think about how, the graphs that we've worked with and like the ways we've kind of gone about counting the number of colors, using the multiplication counting principle. If we scroll back here to like this result here, right? We have lambda colors for one vertex and then lambda minus one for another vertex. We could look at this example or the one, before it here. And it seems obvious, right? Like we just have a collection of factors and each is lambda or lambda minus some number, right? And when we multiply them, we're going to get a polynomial of degree however many, vertices we have. But things get a little complicated here, and so we're going to just show, or things can get a little complicated when we're finding these polynomials. So we're going to show that we always get an nth degree polynomial, and we're going to do this by using induction on the number of edges. And I'll call the number of edges, I'll call that m, because we're using n for the number of vertices. So I'll say we have m edges. So let's let m be the number of edges in a planar graph that has n vertices. So our base case would be if there are no edges. If m is equal to 0, then G consists of n isolated vertices. and the chromatic polynomial is just lambda to the n. Which is an nth degree polynomial. Okay, now for the induction step. Let's suppose, here's our induction hypothesis, let's suppose that the chromatic polynomial for G is a degree n polynomial for all planar graphs with n vertices and k edges. So we're using, this is induction on the number of edges. So here, k is some fixed value, right? But n is not fixed. So as long as my planar graph has k edges, regardless of how many vertices it has, if it has k edges, we're assuming that its chromatic polynomial is degree n. So let's let G be a graph with n vertices and k plus 1 edges. We want to show that its chromatic polynomial is degree n. So we know, we already established this result, that the chromatic polynomial for G sub E hat, if E is some edge in the graph, that chromatic polynomial is the sum of the chromatic polynomials for G and G mod E. And that means, I'm just going to rearrange this equation to solve for this term. So G's chromatic polynomial for G is equal to chromatic polynomial for G sub E hat minus the chromatic polynomial for G mod E. Now, what do we know about G sub E hat? G sub E hat has the same number of vertices as G, right? But we've just removed an edge. If G is a graph with k plus 1 edges, that means that G sub E hat has n vertices, same number of vertices, but one fewer edge. So this has n vertices and k edges. And by our induction hypothesis, this is an nth degree polynomial. Now G mod E has n minus 1 vertices and k edges. Which means that its chromatic polynomial is a degree n minus 1 polynomial. Right, the degree is the number of vertices. So that means that now we'll take this equation here, the chromatic polynomial for G is going to be equal to this difference. So I take the chromatic polynomial for G sub E hat, and I subtract the chromatic polynomial for G mod E. So that means I've got a degree n polynomial here, and this one is degree n minus 1. This is really important that it's degree n minus 1, because if I take a degree n and subtract a degree n, the degree doesn't, maybe those nth powers cancel each other out. But since I'm subtracting a degree n minus 1, I know I'm going to maintain the degree of this polynomial as n. And that's what we wanted to show. Okay. Our next result says that for any non-empty planar connected graph, the constant term of the chromatic polynomial is always 0. And if G has 2 or more vertices, then the sum of the coefficients is always 0. So there's two things that we're showing here, okay? One is that constant term of the chromatic polynomial is 0, so I'll call that the first result. And then here's our second result. If G has 2 or more vertices, the sum of the coefficients is 0. So to start out, let's suppose that G is non-empty, planar, and connected. Then if it's connected, if there's at least some vertices, right? And connected, like if I have at least one vertex, I need more than 0 colors, right? I need at least one color, right? So basically, if I have vertices to color, that means that 0 is an insufficient number of colors. So a way to write that is that the chromatic polynomial of G, if I plug in 0, I get 0. If I have 0 colors, I can't color it. And if the chromatic polynomial is 0, when you plug in 0, that means that the constant term is 0. Okay, so for the second result, if we have a connected planar graph that has 2 or more vertices, then that means we have at least 2 adjacent vertices. That means that we have at least two adjacent vertices which cannot be the same color. That means that if I have only one color available, I can't color the graph. And the way we write that using the chromatic polynomial is that CG of 1 is equal to 0, right? If I plug in 1, there can be no ways to color it. But for any polynomial, right, CG of 1 is just the sum of the coefficients. And so that is equal to 0, which is what we were trying to show. Okay, so we're going to finish out this section by looking at two examples, and really they're the same graph, right? So here we have basically just the cycle, right? A, D, C, AD, BC, right? So just the square. And it's the same graph each time. We're going to look at two different ways that we can use this equation to help us find the chromatic polynomial. One way to use it is that to say that our given graph is a G sub E hat, meaning this was the graph we got when we removed an edge. So let's say that edge was the edge that connected A and B, right? So we think of the graph they gave us as a graph missing an edge. So that means then that G must be this graph with that edge put back. And G's mod E, let's see, if I imagine taking this graph over here on the left and then identifying those vertices, sort of squishing them together, we're going to get this graph. Now all we want to do is get to a point where the graphs that I've drawn that are connected to them, so the ones we're calling G and G mod E, are ones for which we know the chromatic polynomial. We can go through this process a bunch of times. In fact, the idea is you add edges so that you might eventually end up with like a complete graph or something. And so you can do that as many times as you want. You could kind of go through this in a recursive way. Just keep adding edges. But all you need to do is get to a point where I can say, oh, I know that chromatic polynomial and I know that chromatic polynomial, and then you use the equation. So we know from example, we did the example where we found this chromatic polynomial in the middle here. So from example, I think it's 515. The chromatic polynomial for G here is lambda minus 1, lambda minus 2, lambda minus 2. Okay, and looking over here on the right, the chromatic polynomial for G mod E, just by inspection, is lambda minus 1, lambda minus 1, right? I mean, so if I start at D here, once I move down to A, I can't use that same color. Once I move down to C, I can use any color except for whatever color we picked for A. So the color for D is back in the running. So lambda minus 1, lambda minus 1. Now we'll use the equation lambda minus 1, lambda minus 2, lambda minus 2, plus lambda minus 1, lambda minus 1. Now let's simplify this. We have some common factors, lambda and lambda minus 1, so we take that out. And inside, then we have lambda minus 2, lambda minus 2, plus lambda minus 1, and I'm just going to simplify what's in the brackets here. I'm going to expand and combine like terms. So we have lambda squared minus 4, lambda plus 4, plus lambda minus 1, so minus 3 lambda plus 3. So this is the chromatic polynomial, and you'll note that quadratic on the end, that doesn't factor. And so this is actually kind of an interesting result. When we do something by inspection, we just have a collection of factors like lambda minus 1. They're all of the term lambda minus k, right, for some number. And so for graphs where we can find the chromatic polynomial that way, it would kind of suggest like, oh, maybe all chromatic polynomials factor in that way, but they don't all factor all the way into linear factors. So here we see a graph that is not, terribly complicated graph, right? It's just the square. And its chromatic polynomial doesn't factor all the way into linear factors. So I said we're going to do this twice. Again, let's take a look at the same graph. And this time we're going to see the given graph as our graph G, and we're going to pick an edge. So I'll let E be the edge connecting A and D. And so then G sub E hat looks like this. I'm just going to remove that edge, but leave the vertices. Okay, and G mod E, if I kind of squish A and D together to become the same vertex, then that ends up just looking like a triangle, or it is a triangle here. The idea behind this technique is we can remove edges, right? Remove connectedness. Oh, I didn't draw these edges in. And if I needed to repeat this process over and over again, we would eventually get down to the point where we just have isolated vertices, if we even needed to go that far. But again, you just want to get to a point where we know the chromatic polynomial for the graphs that we are related, right? So in this case, G E hat and G mod E. We know both of these, right? If something is just a connected, like a straight line, which is what we have, it's drawn to look like an open box, but it's really just one straight line in the middle here. By inspection, the chromatic polynomial for that graph, if I start at A, I've got lambda choices, and then moving to C, I have lambda minus 1 choices. Moving to B, I again have lambda minus 1 choices. B can be anything except for what we just used for C. And similarly, once I move to D, it could be anything except for what I just colored for B. So I have lambda and then a series of factors of lambda minus 1. That's always the case if your graph is just the form of a single line with just an edge connecting, a single edge connecting the two vertices as you move down the line. Now over here, we could do this one by inspection. This is in fact the complete graph on 3 vertices, but we could see that each vertex is connected to the other 2. So once we use a color, we can't use it again. So we have lambda, lambda minus 1, lambda minus 2. And now we're going to use this version of the equation. We want the chromatic polynomial for G, right? That's the graph they gave us. So I'm going to take the polynomial for G sub E hat and subtract the polynomial for G mod E. So this is lambda times lambda minus 1 cubed minus lambda, lambda minus 1, lambda minus 2. We can take out a common factor of lambda, lambda minus 1. And then inside we have lambda minus 1 squared minus lambda minus 2. I'll expand the stuff in the brackets and combine like terms. So lambda squared minus 2 lambda plus 1, and then distributing that negative minus lambda plus 2. So now we have lambda, lambda minus 1, and our last factor is lambda squared minus 3 lambda plus 3. And that is, of course, the same polynomial that we got before. It had better be, right? It's the same graph, so there should be just one result. And there's our chromatic polynomial. So sometimes we could find a chromatic polynomial just by inspection. Sometimes we might need to break it down into the two related graphs so that we can use that equation. Given how this polynomial looks, right, the fact that it doesn't factor all the way, finding it just by inspection would be difficult.